a commutator. Now, there's two options you can have. Option one is, if this is AC current, then AC current by itself will change direction every half turn. So therefore, the sides swap and AC current swaps as well. So everything is okay, and the motor can still keep on going in a circle. However, if it's DC current, then what you need to do is, you need to have a commutator that is going to change the direction of the current every half a cycle. So therefore, for DC, I have a split ring commutator which can reverse the direction every half turn, and for AC, I just have a slip ring commutator. So these are the basic principles behind the operation of a motor. Looking at a generator, the basic principle behind the generator is Faraday's law of induction, which states that any change in a magnetic field that is, and if I change a magnetic field and I put a coil of wire in the magnetic field that is changing, it will cause a voltage or an EMF to be produced. Stated simply, it says a changing B will induce an EMF, and that EMF can then be used to generate a current. The faster the magnetic field changes, the more the EMF, and hence the greater the current. So this is Faraday's law of induction. Then we have Lenz's law. The difference is, Lenz's law tells you the directional relationship between the induced magnetic field, the voltage, and the current when a conductor is placed in a changing magnetic field. Essentially what it means is this. Faraday's law only stops here. It will tell you that a changing B will produce an EMF. Now, we know that this EMF is now going to produce a current. We also know that current produces a magnetic field. So we call this V2. What Faraday's law says is that only this much. Lenz's law will also tell you that this current that is produced will produce a magnetic field that has to be in the opposite direction. So this new magnetic field that is produced by this EMF/current has to be in the opposite direction to the original magnetic field. Why is that? If you think of the law of conservation of energy, if this new magnetic field was in the same direction as the original one, then what will happen is it would add to it. So means I would have a greater magnetic field, which means I'll have more EMF, which means I'll have more current, which means I'll have more of the generated magnetic field, which will then go back and add to this guy, and the cycle will continue endlessly. So therefore, to obey the law of conservation of energy, this new magnetic field has to be in the opposite direction to this guy. The next concept we're going to have a look at is eddy currents. So eddy currents are almost a consequence of Lenz's law. All eddy currents are circular currents in bulk metal. Alright? So as a consequence of Lenz's law, eddy currents are generated. Eddy currents are just currents that go around in a circle. Now mostly eddy currents transform kinetic energy into heat. A lot of the times this is actually a very wasteful use. You're converting kinetic energy to heat, and essentially, in a transformer, in electric motors, this is considered quite harmful. But however, there are a few useful applications of eddy currents, such as eddy current braking. The last thing we're going to have a look at today is back EMF. Now, let's have a look at the example again, right? Back EMF is the voltage that is produced in a conductor that tends to neutralize the present voltage. What does that mean? Think of it like this. We just learned Faraday's law of electromagnetic induction. What that states is that if I have a changing B, then I will induce an EMF/current. Alright? So a changing B will produce a current. As long as there's a changing B, I'm going to get a current. Let's consider a simple motor. In a simple motor, I have a supply EMF. So I put in some voltage. Alright, that's coming from the power point. This then causes the motor to move. Now, this is due to the motor effect. Now, the motor is essentially this, right? I have a magnet and I have a coil. So because of the supply EMF, this coil is now moving. Now, as this coil moves, it is in a changing magnetic field. Why? Because it's cutting the lines. You know, there's lines going from here, from north to south, and this coil is cutting the lines. Because this coil is in a changing magnetic field, I know that a changing magnetic field will produce an EMF. The motor moves, which produces a changing B, which produces an EMF. This EMF has to oppose the supply EMF, again because of the law of conservation of energy. So essentially what we have is quite similar to Lenz's law. Lenz's law said that changing B produces EMF, which produces I, which produces negative B. Right? This guy says, this guy starts with EMF, which produces a changing B, which produces a back EMF. Lenz's law, changing B produces EMF, produces a negative B. Now, back EMF can actually be used for self-regulating drills. So essentially what happens is, as long as the motor is moving, a back EMF will be produced. If the motor stops moving, then there will be no changing B and no back EMF. Therefore, if a drill gets stuck, if I'm taking a drill and I'm drilling into something and the drill gets stuck, essentially what happens is the motor does not move. If the motor does not move, there is no changing B, which means there is no back EMF. Because there is no back EMF, there is going to be a large amount of supply EMF and the motor is going to burn out. That is the end of all the basic principles we'll be having a look at today. Thank you.